Encima me rodaron esto, los matos.
¿Pero no lo tenías marcado?
No, me rodaron las cajas. Me rodaron las cajas. A ver. Sube un poco esto. Ahí está.
Vale, y ya
Pero vaya a empezar por aquí.
Sí.
A ver.
Sí. ¿Y ellos pueden conectarse y preguntar?
Y ellos en teoría, no lo sé, en teoría podrían chatear. Me da que al menos pueden chatear.
Dígame si...
Perfecto, sí.
Okay.
Vale. A ver si nos ven. Clave, vale.
No. Sí.
Le voy a preguntar si pueden. No. Creo que pueden chatear. Pero hoy solo chatear. Ya lo hacemos bien después para que puedan. A ver.
Vamos a la boca. Solo con señas.
No, después conectamos con Hangout.
Sí, otro día lo hacemos con Hangout y mejor. Vale, entonces. Yo creo que estamos. A ver, solamente me quedaría. Vale, esto es lo que están viendo ellos. O sea que vale, esto es lo que están viendo ellos. Vale, esto es lo que están viendo ellos. Vale, cuidado ahí con el YouTube. Vale. ¿Qué dice María? Espérate, a ver. Voy a llamarlo más rápido. Pequeño retraso aquí. Hola María, ¿qué tal? ¿Viste el último mensaje? Vale, no, el enlace, les puse usen este enlace. Y es un youtuber. Vale, al menos la ven.
¿Habla?
Bueno, si tienen alguna, yo creo que pueden, mira a ver si pueden hacer comentarios en el streaming, no te deja.
Dile que luego conectamos en YouTube.
Bueno, mira, hoy por comodidad, sí, me están oyendo, me estoy oyendo a mí mismo. La ven y el próximo día lo hago mejor y utilizamos Hangout o algo. Vale, venga, hoy calladito, que veo a David muy lanzadito. venga, María. 1 hora menos en Canarias, ¿qué quieres que haga? ¿Qué quieres que haga? Venga, chao.
Bueno, ya puedes empezar.
Yeah, go ahead.
Okay.
Today there is no David Martín. Fortunately.
Okay.
Sorry for the delay.
So thank you, ciao Maria. Hello, I hope you're well. And so I started this short series of basic course in sub-Riemannian geometry, and in the first 2 lectures I gave the basic definitions. I talked about bracket genetic condition, Rashevsky-Chow, the sub-Riemannian distance, and we arrived to the formulation of a necessary condition for length minimizer given by Pontryagin. And today, the aim of today is to provide a link between the Pontryagin extremos and the symplectic structure on the cotangent band. So let me recall. So given a sub-Riemannian structure UF on N, we have defined the sub-Riemannian Hamiltonian. Which is defined on the cotangent bundle as the minimum of u over the fiber over uq of, the maximum of lambda computed on the anchor map minus 1 over 2 normal mu square, and q is the point, the projection of lambda. And we have seen with the small calculation last time, we have seen that when one has a generating family, so if F1, Fm is a generating family for the sub-Riemannian structure, then H is quadratic on lambda, in the sense that it can be computed to be 1 over 2 sum I going to 1 to m lambda computed on the vector field Fi square, where Q always is the projection. So we have seen that the sub-Riemannian structures are characterized by a Hamiltonian being quadratic in the covector. Okay, so let's talk about normal extrema. I don't know which section I was. Here I am on 2.4. I don't know what I left, but normal extremals. Okay, remember what we saw is that a Lipschitz curve on the cotangent bundle, lambda from 0 t on t star m Lipschitz is a normal extremal. We have seen if and only if is a normal extremal. If and only if lambda dot is equal to h of lambda, where this is the Hamiltonian vector field associated with this Hamiltonian function. Well, I don't know if I already stated it like that, but it is using the form of the Hamiltonian. You can prove that the n condition, the normal condition, is equivalent to this. So in particular, this tells you a lot, because as a consequence, you get that when you define, so when you consider the curve on the manifold, so if I define lambda of gamma of t as pi of lambda of t, you get that this curve is the projection of this Hamiltonian here. It is autonomous, right? Does not depend on time. So my lambda of t can be seen as the flow of some initial covector. So it is E, I denote the flow by ETH, lambda 0. So this is the flow generated by the vector field H on the cotangent bundle, and this is the initial data. And as such, as the projection of the solution of a Hamiltonian system, gamma is C infinity. Or moreover, you can compute the norm of gamma, the sub-Riemannian norm of gamma dot of t, and it is equal to 2h of lambda of t. Okay, so remembering that lambda is a solution to the Hamiltonian system, the Hamiltonian is constant on the extrema, so you get that every normal extrema is also has constant speed. So the norm is constant, the length of the tangent vector is constant, and is given by this relation here. It's given by the Hamiltonian on the extrema. Okay, so I have not so yet there is no symplectic structure here, but here it is going to arise. So let me recall before what is a characteristic curve of a two form. So given as a manifold n, and omega a two form on n, we say that a curve gamma is a characteristic curve for omega if it belongs to the kernel. If gamma dot belongs to the kernel of omega at gamma, or equivalently, if omega gamma dot vanishes. Okay? So, we can now give the geometric characterization of normal extremos. So, proposition, which is a geometric characterization of normal extremos.
Omega is any two form.
Yeah, this is just the definition of characteristic curve. Yeah,
Okay.
any two form. And now I am using this notion on the cotangent bundle with the symplectic form, of course. So, so let's see be a regular value of the Hamiltonian of H. Then a Lipschitz curve in the on the H level C. Then a Lipschitz curve lambda in the cotangent bundle and belonging to the, so on which H is constantly equal to C, H minus 1 of C, is a normal extrema, is a characteristic curve of sigma, so the symplectic form restricted to this level, if and only if lambda is the reparametrization of a normal extrema. Lambda is a reparametrization of a normal extrema. So normal extremos arise as characteristic curves of the symplectic form restricted to a fixed level of the Hamiltonian. So to understand the situation, and since it is doable, I'm going to do the proof. So why we assume C to be a regular value? Because we want this to be a submanifold in order to be able to restrict to the tangent of this submanifold. So C regular value. Well, H anyway is a smooth function, so almost every C is a regular value for H. Then H minus 1 is a 2n minus 1 smooth submanifold in P star M. So I can define, given a covector lambda in H minus 1 of C, I can define T lambda of H minus 1 of C. And it is a 2n minus, it is an hyperplane. It is an hyperplane in T lambda P star M.
This H is this, no?
The Riemann one.
Ah,
Yeah, this one.
Okay.
Okay, I have a hyperplane, and so let me call this set E lambda. Since it is a tangent to a sublevel and C is a regular value, we have that d lambda of H vanishes identically. The differential is 0 on this set because, by definition, by construction. Now we consider sigma, and sigma is a skew symmetric and non-degenerate, which means that if I restrict to a space which has to the space E lambda, so considering sigma restricted to H minus 1 of C is means to this notation means I'm restricted to E lambda. And since sigma is skew symmetric and E lambda has dimension 2n minus 1, the kernel of this object is going to be one dimensional. There is no other possibility. Since dimension of E lambda for 2n minus 1, then the kernel of sigma restricted to E lambda has dimension 1. And by definition, it is the skew symmetric. By definition, the kernel. So let's say it is the linear span of some vector psi. Okay. From some psi belonging to T lambda star n. Then, by definition, this guy is the set of omega in T lambda T star n, such that they are skew symmetric to, so sigma omega psi is 0. For every, I'm sorry. I need this condition. Yeah, okay, this is true. And what I can say now, I use the fact that the Hamiltonian vector field is characterized by the symplectic form as by the following identity. So recall that. So recall that sigma h of lambda is equal to d lambda h by definition of Hamiltonian vector field. So we have that when we restrict to E lambda, this guy, both sides, here we have 0 because I am on a level. And here, what I'm saying is that so that sigma omega h of lambda is equal to 0 for every w on E lambda. So mainly what I'm saying is that the kernel is generated by this vector here. Kernel of sigma restricted to E lambda is generated by h1. So a curve lambda belongs to the kernel. So lambda dot belongs to the kernel if and only if it is a multiple of this vector. And lambda dot belongs to the kernel if and only if lambda dot belongs to this one. So that's why I put reparametrization, because it is definitely a function. Okay. Right.
it's not important.
Yeah.
The last statement in the blackboard.
Yeah.
It's not right, I think so, because
there must be E lambda somewhere, I guess.
No, but
or the square root.
Because the kernel of the symplectic structure.
Yeah.
When you restrict to E lambda is of dimension 1, so
yeah,
it's just it's generated.
Yeah. So
it's not
I think I have to put symmetric.
Yes.
Okay.
It is.
Yeah. Yeah. Thank you. Of course. Yeah. So by this I mean
this is
the skew symmetric to this guy.
This is the
which is
complement.
yeah. Thank you. Okay. So normal extremos are characteristic curve of the symplectic form. So what can we say about abnormal?
Yeah.
Mm-hmm. So what can we say about abnormals? Let us recall what is the condition on abnormal extremas. So again, I'm taking a generating family. So sorry, from the statement here again, you see that actually generating family doesn't come out here. You have your Hamiltonian H, which has a simple form when you use a generating family, but H here I am not using the particular form. Okay. And anyway, we have seen that the Hamiltonian is something which is intrinsically associated to the structure. Okay, even if when I write it explicitly, I make use of a generating family. That's what it's saying. So remember that our H of lambda was some 1/2 I from 1 to n lambda fi of q square, and so we have already called these functions here hi. So 1/2 hi of lambda square. Okay. And we have seen that lambda is an abnormal extrema if and only if lambda dot equals to some linear combination of the vector field as Hamiltonian vector field associated to these Hamiltonians, but the linear combination is made with this coefficient who are time dependent, controls which are time dependent. Okay. So now look, if I have an abnormal extrema and the condition A, if you remember the condition A gave you that hi of lambda was 0 on the curve, on the abnormal extrema. So this tells you that on abnormal extrema, so if lambda abnormal, then the sub-Riemannian Hamiltonian vanishes identically on the curve. So abnormal extrema belong to the 0 level set of H. And since H is quadratic, 0 is never a regular value. H quadratic, 0 is never a regular value. So in order to be able to restrict our symplectic form to the level 0 level of H, I'm going to need some conditions
About
to get this level
the image of,
in order for it to
good
be
condition.
So the good condition is the following. Well, the good one condition is the following. So one condition is the so-called is saying that UF is regular of rank R if given a generating family F1, Fn, the linear span, so the distribution is of rank R at every point. So the dimension of F1 of Q, Fn of Q is equal to R for every Q in N. So I'm saying that when I take a generating family, the dimension of the space they generate is constant on the manifold.
This is a usual condition, or this is a strong condition to remain.
This is almost like it is equivalent to say, I think, that it has constant rank. So when you have some bundles or so which is not the most general, but it is. But many
in many cases.
The class is very big.
Yeah.
The class of submarine structures you have. The kernel groups are here. Lie groups are here.
Sure.
So,
but is there any characterization without using the generating family?
No, you're gonna see in the proof where this. Without using the generating family. You mean in this definition?
Yes.
Well, I am. I think you can say that it is constant rank.
So see the rank is constant.
Okay.
This condition for any generator.
I think this is equivalent to saying that the distribution has constant rank. But then in the statement, it is very useful to have this global generating family.
I understand, basically because of the definition in this case, even for H.
But it is the same as saying that this is equivalent to say that rank of V is constant. But I'm not giving, I'm not prescribing the rank of this.
No, of course.
Okay. Or nor I am imposing that this is injective or anything.
No, sure.
I'm only asking that the rank is constant.
This is not regular.
Yeah, sure.
This is at the base of no.
Okay, now in this case, given a regular structure, since this dimension is constant, the zero level is indeed a smooth submanifold. Why? So if I take h minus 1 of 0 into star m, it is given by covector such that so it means that recall that h of lambda is the sum of the hi lambda square. Okay, so in order for h to be 0, I need all the hi to be 0, which means that lambda annihilates all the vector fields. So lambda, let's say, let me write it like that, annihilates fi of q for every I. And since this space has constant dimension, this guy is now, it is a smooth manifold. And since the dimension of phi is constant, h minus 1 of 0 is a smooth submanifold of corank R. In this part. Okay, so I can now give the statement, which is the one you expect. So geometric characterization of abnormal extrema. So if UF is a regular structure, I take a Lipschitz curve in the 0 level of H, curve lambda in the 0 level of H, is a characteristic curve of the symplectic form restricted to H minus 1, 0, if and only if it is the reparameterization of an abnormal extreme.
The same, no? It's the same of the case of.
Yeah, it's a unified way of seeing things. Only here, so the level of the Hamiltonian here is 0. Up there it was a regular value, and yeah, it is precisely a unified way. Only here we need this regularity because we need this. So that's how we can restrict the symplectic form, and that's how also. We can compute the kernel. So because we need the kernel at every point to be a vector space.
And the proof is similar, or you can
Yeah, I'm going to do it. Yeah, it's the same. The proof is the same. So the proof. So let me call N the submanifold H minus 1 of 0. So the kernel of sigma restricted to N is by definition the skew orthogonal, which was the one I was missing on the first proof, the skew orthogonal of the tangent to N. And so it is the set of omega belonging to T lambda and T star N, such that sigma omega lambda is equal to 0 for not lambda, sorry, sigma omega v for every V in T lambda n. So now, who is the space T lambda n? It is, by definition, since n is a level set of H, it is by definition a set of V in T star, in T lambda, T star n, such that d lambda Hi applied to V vanishes for every I, and I can use a symplectic form here to say that this is equivalent to sigma V Hi equal to 0. Okay? Sorry. And since this Hamiltonian, since the Fi are linearly independent, since the dimension of the space generated by the Fi is constant, also the dimension of this space generated by the Hi vector is constant. So this is the span of this means that sigma is orthogonal, vanishes on the span of the Hi. Okay, so taking the skew orthogonal, we are done. So this is equal to the span of H1, HM, skew orthogonal. And now, so what you have, taking the skew orthogonal here, so gives you that the kernel is equal to this linear span here. It's basically the same, okay? Only for the, and also it is a nice way to see things, because for abnormal the kernel was one dimensional, so you had one Hamiltonian vector field, and here you have something which has a dimension r. So in principle, something which is generated by different vector fields. So now a curve gamma is a characteristic curve, lambda, characteristic, restricted to n, characteristic, if and only if lambda dot belongs to the kernel, which means that lambda dot is a linear combination of this guy. So lambda dot equal to sum of ui of t Hi. And what I was saying is that it is nice that since this kernel here has dimension greater than 1, and a priori you have that something non-autonomous appears here.
Mm-hmm.
Okay, so and this is equivalent to say that is a parameterized. Okay. Mm-hmm. And also for this regular structure, and from this characterization of abnormal, you can see that abnormal extremals only depend on the distribution and not on the sub-Riemannian norm, because they are, so remark, when UF is regular, abnormal extremals are covector annihilating D, if you wish. So satisfy lambda belonging to the orthogonal. So they only depend on D and not on the norm. They only depend on D. Depend.
So, question.
Yeah.
Maria says, bueno, te lo digo en español, para no estar traduciendo con la cabeza. Que el hamiltoniano que tiene para las abnormales, ¿de dónde viene? The Hamiltonian that you define for abnormal, where does it come from?
It is the same, only that this was the statement. I can give you. Yeah, I'm gonna write it down. Where is this? For abnormals, what we have seen is the following. That for abnormals, they are you have a non-autonomous Hamiltonian if you wish. You can write them like that. With this hi being lambda fi. Maybe I can give you the statement. The very first statement. It is. If you remember, the very first statement was that when you have an admissible curve, so let gamma be admissible, which means that gamma dot is equal to sum of ui this fi. If you call P0t the flow associated to the controls ui of this, so the flow associated to the vector field, the non-autonomous vector fields that associate with Q F, so sum of ui of t fi of q. This is an autonomous vector field. You can consider the flow defined in a neighborhood of the initial point of gamma. Then this equation can be seen as lambda dot equal to p0, lambda of t equal to p0 t minus 1 star lambda 0. The Hamiltonian is time dependent for the so this is for all admissible curves. Then for normal, what you have is that the UI you can compute them as a feedback, and so the Hamiltonian becomes autonomous. But for the abnormal, you cannot do that in general. I don't know if I answered your question.
I don't know. Let me ask.
When you say that if lambda is a normal extremal, then it implies that lambda belongs to the orthogonal.
This I mean orthogonal by duality. This I mean just mean that
the annihilator.
Yeah, the annihilator. This is what I mean.
Annihilator.
Yeah, not Subrahmanian orthogonal. Yeah. doesn't make
A ver si entiendo la pregunta de María. Hay una parte aquí que no queda muy clara. Ella dice que los controles no están determinados para las abnormales.
Claro.
Pero para que salga cuadrática los toma igual a h sub i, que es lo que pasa en el caso normal. ¿Que por qué? ¿Está bien preguntado, María? Esperemos que sí.
But wait, yeah, I understand. So maybe I have to. Okay. I am arriving. So the sub-Riemannian Hamiltonian itself is well defined, and it is this function here. We have it is 1/2 sum of I'm gonna put it like that, hi of lambda square. Okay, where these hi are the dual to the generating basis. Okay, the fact is that normal. The condition for normal extrema is that ui of t is equal to hi. Okay? And the condition for abnormal is that hi of lambda, so this is for every I, and hi of lambda is 0. Okay? So somehow you cannot you're not using this Hamiltonian to compute so the Hamiltonian system associated to that only works for the normal case.
Yes.
For the abnormal case, your Hamiltonian vanishes identically, so it is not the dynamic equation for lambda in the abnormal case is not the one you obtain. Well, if you take the one obtained from H, you're gonna have 0, which is false in general for abnormals as well. So you have to keep in mind these two conditions, I think. I don't know. Yeah.
So, if you have a normal extrema, then the control in general are not determined.
Exactly.
Yes. This
Exactly.
the point.
That's the difficult. Yeah.
Yes. Because
Go ahead.
Yeah.
I'm waiting for the answer.
Yeah.
It was my mistake that I didn't read all the parameters.
And the converse, if you have a lambda in the annihilator of D, then it is an abnormal extrema, or what is the condition? Because when you put
I think so.
I think so. Yes, it's.
Well, if you need this a little regularity, but yes.
Yes.
Yes. Yes.
Yes.
If you have a curve in the cotangent, which is a curve which has a good, let's say not a curve, a vertical. Well, when you have a vertical, you have a trivial curve on end, okay?
Yeah.
Which you can have, which can be an abnormal extrema. This is possible, but let's say you have a curve which is transverse.
But if you have a curve in the annihilator, this is a normal extrema.
Abnormal, yeah. Yeah.
Right.
Wow.
María aprueba la respuesta. Puede continuar.
Okay. Thank you, Maria. Okay, maybe so. I'm gonna end this session with an example.
Yeah.
And yeah, tell me.
If I remember correctly, there is a relation between contact geometry and Riemannian structure. Perhaps the sample is related with
well, I was going to talk about Heisenberg, which I think is contact. So, contact geometry is when you have a differential form and you consider the kernel, right? So when you fix of course, in this way you get a distribution which is for constant rank and as codimension 1, and then you fix a metric on it and you have a sub-Riemannian structure. So this is a perfect way of constructing
Riemannian
structure.
structure.
Yeah. And I am not. I have not studied them yet, but in the contact case, I think. Well, I'm sure that there are results known about abnormals. I'm not sure if they are completely absent in general, but I'm gonna check it down. Check this down. No, they are in general. Probably it is not true that if the structure is contact, then there are no abnormals. But under some other condition, maybe yeah. I don't know. I have to check this. But for sure, the situation is also from a computational point of view. It is easier when you have because you have not only you have constant rank, you have corank 1, and so this means that the missing direction is only 1. So this means that. Generically, yeah. So you can do things. It is a context which is wide, and in which you can do things. So here. There is a nice way to see Heisenberg as a sub-Riemannian structure coming from an isoperimetric problem. So let me do that. I don't know if you are familiar with isoperimetric problems, but so let's take M bar equal to R2. And let's take a one form on R2. This is general, that's general. Then I will go to Heisenberg. I take a one form.
And M is any manifold?
No, sorry, the same. Of course, the same. So let's say this is just let's say isoperimetric problem. And Heisenberg will be well, it will be the one where this is up to. I take as a Riemannian surface. M bar is a Riemannian surface. So for Heisenberg will be R2, also with some Riemannian structure on it. And I take a one form, and I take a real number. So the isoperimetric problem is the following. It is a problem of calculus of variations. So it is given two points, Q0 and Q1 in M. Find the curve which realize the following minimum. The length of curves, so gamma curve in M in bar M, joining Q0 and Q1, with prescribed integral equal to C. Integral of A over gamma equal to C. So why isoperimetric? Because you are prescribing the perimeter of this curve computed with respect to this one form. Okay, so this problem we can construct a sub-Riemannian structure on the manifold n equal to bar m cross R. It is possible to construct a sub-Riemannian structure on M in such a way that this just becomes find the sub-Riemannian distance between 2 points here, which are related to this one. So I'm going to do this quickly. This is just a motivation a motivation which is quite, let's say, which comes both from Riemannian geometry and from calculus of variation to introduce an example like the Heisenberg group. So the sub-Riemannian structure, how it is defined. I define it as, so I'm taking as a distribution. I need to say what is the distribution and what is the, okay. I'm going to call Z the coordinate here and Q the point here. So I'm defining omega, one form over R over M by omega equal to dz minus A. Okay, this is a contact structure. It is a contact structure. And so D is defined as the kernel of omega. And how do I define the sub-Riemannian norm? I take for a V in D.
Roberta,
Dígame.
¿la curva tiene que ser cerrada? Preguntan por aquí.
No. Here no. Well, I cheated a little bit saying that this was the perimeter because actually this was not a closed curve. Yeah, I was cheating if you wish. No, yeah. Yeah, no tienes que ser cerrada, no. No tiene que ser. But I understand why she asked it, because I said that this was the perimeter. So one can think of a closed polygon, not yes.
Por área significa realmente es integral. Lo que estás llamando área realmente es integral.
Sí. Because it is called like perimeter because the dual problem it is a problem of perimeter. This is a problem of prescribed area. Yeah, must be like that. Okay, so for vectors, this was Dido, right? Dido's problem. Okay. So the norm is defined. Sorry, not.
Como un poquito más de
yeah. No, the one who she was mentioning was Dido, which is Dido.
Yeah. Es que el problema isoperimétrico clásico es ese, tú tienes una curva cerrada, tú tienes un área determinada y entonces tienes que buscar la curva de tal manera que...
well, because what was misleading me is that isoperimetric is the same perimeter, okay?
Yeah,
that's why I always think of it as prescribed perimeter. Well, it is the dual of this guy which is prescribed perimeter.
Un poquito más general, porque está suponiendo que la curva no es cerrada, o sea que es general, ¿no? Un poquito más general.
So we define the sub-Riemannian norm as the norm of the projection of P star V. What is it? P1 star. So as the Riemannian norm of the projection of this V of the first factor, I use the Riemannian structure on bar N to get the norm. And how? So and if pi is this pi 1 is the pi 1. And so given a curve here, which connects the 2 points and which satisfies the condition, I can define a curve. So let's say given gamma bar, a curve on the Riemannian part, we can define z of t equal to the integral of this gamma bar restricted to 0t of the one form, which is a simple integral from 0 to t, small t, of a of gamma dot ds. Yes. And with this definition, if I take the curve gamma of t, which is now a curve in m bar cross r, equal to gamma bar Z of t. What I get by construction is that gamma dot bar belongs to the kernel of omega, because Z dot is precisely equal to A of gamma bar. Okay? So it is an admissible curve for the sub-Riemannian. This gamma here is an admissible curve for the sub-Riemannian structure. And the length of gamma coincides with the length of gamma bar by definition, because I have defined the sub-Riemannian norm as the Riemannian norm of the projections. Okay? So with these notations, you get that the isoperimetric problem is equivalent to the following one. So which I call, let's say, sub-Riemannian problem. Given Q0, Q1 in the Riemannian manifold, minimize the length, this time let's say sub-Riemannian length of curves connecting gamma connects admissible and connects Q0 0 to Q1 C. So the prescribed area appears as the second coordinate of the second point, and here I take 0, which is just the sub-Riemannian distance, as you know, as we have defined it. Okay? Okay, now Heisenberg is the case where M bar is R2. Where I take coordinates x to x, y, and I take as one form. I don't want to be wrong. It is 1/2 x dy, just like this. I see. Minus y dx. Okay. So here, so Heisenberg as manifold is just R3. It's just R3. And on R2, of course, I take the Euclidean matrix. So let's say G equal to dx squared plus dy squared. And so if I take the orthonormal frame for the Riemannian part, it would be d of global orthonormal frame for R2 is d over dx, d over dy, and I can construct an orthonormal frame on the Heisenberg by taking, let's say, f1 of f1 equal to d over dx, which is the orthonormal part of on R2, plus a computed at f1. Yeah, plus a of f1, sorry, of d over dx, d over dz, and f2 d over dy. Yeah. It's invariant with respect to the product of you choose. You need to choose the good product or nothing. Yeah, it's that invariant. D over dy. I'm sorry. So explicitly, this is d over dx plus 1/2 minus 1 y over 2 z, and this is e over 1 plus x over 2. So if you wish, I can end by computing, but by showing that there are no abnormals here.
Mm-hmm.
So that we can enter the explicit in the conditions. So who are the functions? H1 of lambda, it is lambda f1. So I take x, y, z coordinate on the, so lambda x, lambda y, lambda z on the cotangent. So this is lambda x minus y over 2 lambda z.
Lambda x and lambda z are the momentum.
Yeah. Okay. It's the dual coordinate to it's the x divided z. Okay, so let's assume lambda be a non-trivial abnormal extrema. What I mean by non-trivial, I mean that the projection on the Heisenberg group, so the projection on M is not a point, okay? So in particular, let's say that, and I'm taking it starting at the origin. You have already guessed that the structure is left invariant, so to study left-wing misers, it is sufficient to study those starting at the origin. So, well, I'm not completely, so whose projection starts at 0, 0, 0. Okay, so what is the equation for lambda and for the curve down? So I assume my admissible curve gamma satisfy gamma dot equal to u1 f1 plus u2 f2, and requiring it to be non-trivial is equivalent to asking that the two controls do not vanish identically. Okay, so this equation, it is for the part on the manifold, and it can be explicit. We can explicit it as x dot equal to u1 y dot equal to u2 and z dot equal to minus y over 2 u1 plus x over 2 u2. This is the part on the manifold, and the part on the cotangent fiber is lambda dot x. So remember, I have to take sorry. I have to take, so lambda dot is minus lambda x. Oh wait, so what? Instead of going to the equation, let me use the fact that I am on an abnormal. Abnormals, as you remember, means that H1 of lambda is 0 and h2 of lambda is 0. So this means that lambda x minus y over 2 lambda z equal to 0, and lambda y plus x over 2 lambda z vanishes identical. Okay? Now, if these two functions vanish identically, when I take the technique is to always do the differentiate with respect to t and see what condition, further condition one gets. So if I take the further condition, what I get is that, so recalling that this was lambda f1 and this is lambda f2, since f1 f2 are linear independent and the controls are, the pair of the control is not 0, you get from d over dt of these conditions, you get that lambda f Lie bracket f1 f2 is 0, which means that this Lie bracket you can compute it is the third direction. So which means that lambda z is identically 0. Okay, so from this condition you go, so we have taken the first order condition for the abnormals, we have differentiated them, and we have obtained this condition here. Now if I plug this up here together with 1 and 2, this gives that lambda x must vanish identically and lambda y as well. Okay? But this is a contradiction. As you remember, for abnormal extremas, you had also the further condition that the covector cannot be 0 on an abnormal extrema. But lambda must be non-zero on an abnormal, hence a contradiction. So there are no non-trivial abnormal extremas. Okay?
So before we say that if you have a Q on T star n, which is in this case the rank of the structure is constant. So if you have a Q in the annihilation of the distribution, so you have a normal streamer, but now here.
But wait, I am saying non-trivial. The only lambda here that annihilates is
lambda c, lambda equal to 0.
No, wait.
It's not possible.
No,
You assume that.
No, sorry. So what I'm saying is that if you take the orthogonal, since the distribution has dimension 2, if you take the annihilator, sorry, not the orthogonal, the annihilator, you have a third, and if you take a covector in the annihilator, what I think is that you get something. You stay on the same fiber. You stay on the same point. So you have an extremal which is correspond to a trivial curve on the manifold.
Yeah.
So if you ask them to be non-trivial, you won't have any.
Yeah. But at the beginning, a priori, you have a normal streamer which belong to the annihilator of the distribution, right?
Yeah.
But when you project to the this is a Q on T star. I am confused with this.
Yeah, I understand your question.
Yes, because abnormal streamer belong to the annihilator of the distribution. In this case, the annihilator of the distribution is of rank 1.
Yeah.
So you have a abnormal streamer. There is something I don't understand.
Yeah, I understand your point.
Because the important condition, perhaps here in this computation, the computation of the Heisenberg group, perhaps we miss this condition. It's just the composition of H1 with the lambda and the composition of H2 with the lambda is 0. So this computation.
No, this is okay, right?
Yeah.
This is to understand as a computation. Yeah. What I didn't specify here is that here I'm using, when you differentiate with respect to t again, you are using, to get this condition here, you need the control to be non-trivial. If you have trivial control, I think that when you think of the annihilator, this corresponds to a curve which is trivial. So it is an abnormal extrema, but it is trivial. Yeah. It corresponds to a trivial curve. Yeah. It corresponds to a covector which is always the same fiber, on the same fiber of the cotangent bundle. Okay.
And this curve doesn't produce
a curve of
trajectory
downstairs. Yeah. I think that's the answer to your question.
Note that in order to obtain the result, that you have not non-trivial and normal experiment, it's important that the condition, the A condition,
yeah,
H, the composition of H1.
Yeah. What one does when you have a control system, an optimal control system, when you have some Riemannian, let's say when you try to look for solution to the optimal control system, the first thing to do to compute abnormals is differentiate this condition with respect to t and see what happens, and see if somehow either you can compute explicitly the control, because sometimes you get something when you derive this guy with respect to t, the control appears linearly. So if the coefficient you have of the control, for some reasons, you can prove that it is not zero on your curve, then you can compute the control, and in some way you have explicitly your abnormals. Or if you cannot, that's the bad situation. I mean, you have to differentiate more and see.
Yeah, I see.
Okay. Okay, yeah. We can, after you give the short
introduction
to Poisson, we can do. I can continue Heisenberg maybe with the normal extremas and go to groups.
Mañana tengo clase, lo que pasa es que mañana a las 8.
Primero de todo vamos aquí a despedirnos de los amigos, digan adiós.
Chao.
Adiós. Chao, muy buenas preguntas, chao.
Mira que la próxima vez lo organizamos mejor, ya lo importante.
Yo mañana